Okay guys, so in this week's video, what we're going to talk about is continuity, right? And this is going to be the last video for this unit that's presenting new content. Next week is going to be just a review video, and then that'll be our last video. So sad. So like I said, this week we're going to talk about continuity, and so this is going to put everything that we've been doing all together, and so these are the conditions for a function to be continuous. And so this just says that a function f of x is continuous at this x value a if these three different conditions are met. Okay, so it is imperative that all three of these have to be met. Okay, so I will go step by step through these and then also represent them graphically, so you just have a better idea of what's actually going on in each of them. And so it's not just a bunch of like jumbled words coming at you, right? So for our first one, it says f of a exists. That just means that our function actually has a y value at that point. Okay, so if we have our little graph here, and this is just some x value a, we know our f of a exists if there's a closed circle at that point. Okay, so that's all that means. The second one is talking about the limit. We need the limit as x approaches a of f of x to exist as well. So here is our a, and so we can have it at an open circle or a closed circle, but remember what we need to have for our limit to exist is it needs to exist from the left and also the right. They need to be the same value. They need to be approaching the same value from the left and the right. So this is step 2. This tells us the limit exists. And so then the third thing for a function to be continuous is that we need the function value, we need f of a, to equal our limit. Okay, so what this would look like if we have our graph, basically we're just combining these two into one. So we have a, so this is our f of a. This also needs to equal our limit. Okay, so this means our function value is right there, it's defined, and then our limit is also going to equal that value. The way I like to think about continuity, the way I was taught, is that a function is going to be continuous if you can draw it without picking up your pen. Okay, so you can draw this whole thing, fill in your circle, keep going, just draw. You don't even have to fill in the circle, you just keep going. You don't have to like pick it up at any other point. So an example of something that would not be continuous will look kind of like this. So we have our function, or we have our graph. Right, we're going to have our little a value. So let's say this is our limit. So the limit exists, right? But our f of a is all the way down here. So if we go to draw this, we can't keep going. We'd have to pick up our pen, fill in the function value, then come back and continue our limit. Okay, so this is not continuous. Okay, that's an example of a function that is not continuous, whereas this, since all these criteria are met, this one is continuous. Okay. Alright, so now I'll actually go into examples and kind of do this a lot more algebraically. So, again, I'm just going to label it steps 1, 2, and 3 so you can clearly see, like, that's what I'm doing. So, first step, we need to find our function value. So we want to find f of 4. So we're just going to plug it into this function. We have 3 over the square root of 4 minus 4. That gives us 3 over 0. This is a problem, right? This means our it's undefined. There's no value. So this is already violating that first condition, right? So our f of a does not exist. Therefore, this is discontinuous. Okay? It's that simple. The second one, I remember last week in class and in the videos, I kept talking about how this line right here, the whole x equals -1, using these sort of conditions, this was irrelevant until this week, and this is why. So, first step, we need to find f of -1, and that's what this line is telling us. This is saying when x equals -1, our y value equals 0. Okay. Second step, we need to find our limit as x approaches -1. Okay. So again, we're just, since this is the way it's set up, instead of having inequalities, we are always going to use the not equal to function. So, and I'm just going to go ahead and I'll factor this right away. This top is going to factor as x plus 1, x minus 1. That bottom stays as x plus 1. We know we can cross things out. So now we can go ahead and substitute. Negative 1 minus 1 gives us negative 2. So function exists, limit also exists. On to the third step. We go to check, does our function value equal our limit? 0 does not equal negative 2. Therefore, this is discontinuous. Okay. On the homeworks, you'll have to identify why. It's all just multiple choice. It's just identifying, is it because the function does not exist? Is it because the limit does not exist? Or because the function value does not equal the limit? Okay. Right now, I'm just stating if it is continuous or not. All right. Number 3 is actually the same function, but just tweaked a little bit from that top one. Okay. So again, first step, finding our function value. We need to put in f of negative 1. That's going to give us, already tells us, negative 2. So that's good, that exists. Second step, we need to find our limit. Limit as x approaches negative 1. Again, I'm going to go ahead and just factor this right off the bat. X minus 1, x plus 1 in the bottom. Then we have those x plus 1 terms. We can go ahead and cross those off. So our limit is going to equal negative 1 minus 1. That gives us negative 2. Okay. Last step, we have negative 2. That's our f of negative 1 equals, oops, that's a negative 2. Negative 2. So that's good. That means that our function is continuous. About time we got a continuous example, right? Everything was discontinuous up until this point. So yeah, it's really important that you do go step by step by step. If you guys do like the worksheets and like send me your work by chance, I do want to see stuff like clearly labeled. If we were in person, I would be asking the same. This is how I'll do the examples in class. If you ask for help, this is exactly how I'll do it. I will lay it out step by step by step, just so you can easily see, all right, this is the function value. Does it exist? Yes or no? Go to the limit. Does the limit exist? Yes or no? Third step, are our function value and our limit the same? Okay. It's a very, very just systematic sort of approach to these problems. All right. Last example. This piecewise function is written a little different than the ones above, but don't fret. So we're looking when x equals 3. First step, we need to find f of 3. So since this one did not just give us straight up an x equals 3 like they did above, we need to use when we have the or equal to. Okay, so x is less than or equal to 3, so we're going to plug it in here. Square root of 3 plus 1. That's going to give us the square root of 4, which equals 2. Next step is our limit. And this one we're going to have to do from the left and the right, because we have our inequality. So the limit as x approaches 3 from the left, we're going to use this function right here, right, because x is less than 3. Think less left. So square root 3, x plus 1. My bad. We can go ahead and substitute. Square root of 3 plus 1, again, is going to equal 2. Now we need to find the limit from the right. We're going to use this function down here, right, because x is greater than 3. So 5 minus x. When you substitute in, you get 5 minus 3, and that equals 2. So since our limit from the left equals 2, and our limit from the right equals 2, that means our limit as x approaches 3 of f of x equals 2. So that's still just our second step with our limit. Third step, we need to see if our function value equals our limit. So f of 3 equals 2. Our limit of f of x equals 2. That's good. So that means that our function is continuous at x equals 3. Okay. Again, they're not anything too difficult. They are just really, you got to go step by step. You need your function value and you need your limit. Yeah, all of these are going to be doing algebraically. When we get to discontinuities, we'll be working with graphs a little bit, but so we can identify the discontinuity, and we'll get to that in a second. But when you're actually just given a function, we just want to know, is it continuous or not, and explain why. Okay, so hopefully not too bad. Next, we're going to talk about types of discontinuities. Okay, so now we can actually get into it where when our function wasn't continuous, we can figure out what's going on. Okay, so there are 4 different types of discontinuity. The first one is called a jump discontinuity. Okay, and so that looks like when you have a function and you are graphing it, right, goes to a point, and then it jumps up and carries on from another one. So again, you know a function is continuous when you're looking at a graph if you can graph it without picking up your pencil or pen, whatever, right? So if you're going and you're trying to graph it, you go, go, go. Oh, you got to jump up, pick up your pen, come to the next one, and graph it. So that's one type of discontinuity. Another is removable. This is also referred to as hole. That happens when you have a function, right? Looks like that. There's a hole in it, and your function value is defined below. So like this was the example I kind of started with. Your function value exists, your limit exists, but you can't graph this without having to pick up your pen to identify your function value and then continue your graph. Okay. Third type is asymptote, or also called infinite. It's exactly what it sounds like, right? It's when you have an asymptote and your function gets close to it, right? Looks something like that. You get the gist. But so you graph it, and then you have to pick up your pen to jump over that asymptote and then continue the rest of your function. Okay, so when you actually have like a visual, I think it's pretty easy to identify the type of discontinuity, just so because you can clearly see and just know like if something's continuous. You can physically trace it and see, oh, can I go the whole way without picking up my pen? Yes or no. The last type is actually a little different. It's called endpoint. And so that happens when you literally just have an endpoint and it looks like that. So the reason that counts as a discontinuity is because, again, for a limit to exist, it needs to exist from the left and the right. And so if you're trying to find the limit of this on the left, that limit doesn't exist. Okay, so that would violate the second condition for continuity, which are the ones that are listed on the front. Okay, so yeah, these are our 4 types of discontinuities. Now we're going to go ahead and like work with some graphs to identify them. First one, is f of x continuous at x equals -1? So I'm going to go step by step. Remember our first one, we want to know what is f of -1. Okay, so if we look, that has a value of 2. Alright, second step, we need our limit. So our limit, as x approaches -1 from the left, that equals 1. The limit as x approaches -1 from the right, oh, that equals 2. This means our limit doesn't exist. Okay, so no, the limit as x approaches -1 of f of x does not exist, right? Because that left limit equals 1, our right limit equals 2. So that's going back to week 1 of understanding our limits. So now we're going to go ahead and identify the type of discontinuity that this is. So if we just go ahead and look up here, you can clearly tell from these rough sketches that I made which one this is going to be. So if we look, you're going, you got to jump up and then finish your function. So it's going to be a jump discontinuity. And so then the way we're going to talk about this, about your function being continuous, is the way I like to think about it is these intervals are going to consist of the parts of your function where you could draw it without picking up your pencil. So hopefully as I go through this, that will like make a little more sense. That sounded a little funky. But so it's going to be continuous. So if you think you're drawing your function all the way from negative infinity, you can draw it. And then once you get to -1, that's where you have to pick up your pencil. So the first interval is going to be from negative infinity to -1. Okay. Second interval, we can start at -1 and keep going towards positive infinity, right? And so that we will never have to pick up our pencil again. So that means our next interval is going to be -1 to infinity. Okay, and so the reason that this is not getting a bracket, even though this is a closed circle, is because this we're talking about, if we were to put a bracket on that, that would mean that it's included in the interval, and so then this whole thing would essentially be pointless, right? But this is saying, by having both these parentheses, that's saying there is a discontinuity at -1. Okay, so like we identified earlier, the discontinuity is a jump discontinuity because the limit does not exist. So that's why we have to use parentheses for these. Okay. Next one, number 2. We need to think, is f of x continuous at x equals 2? So we can just sketch it. You can go, can we draw this whole thing without picking up our pencil? Oh, nope. We have a hole here. Remember, that type of discontinuity, no, I'm skipping, whoops. That type of discontinuity is called removable. But so the reason it's not continuous, if our first step, right, is to look for our function value, f of 2. We go to 2, except there's a hole at 2, right? So that means this is undefined. There is no y value for when x equals 2. So that's the reason that this is not continuous. F of 2 does not exist. Okay, so it violates that first condition. Like I said, this is removable. Now we need to do our open intervals. So again, think back to this example right here. Our open intervals are the intervals on which we can draw our function without having to pick up a pencil. So we can draw it starting at negative infinity all the way up to 2. Negative infinity to 2. Then we can go again from 2 all the way to positive infinity. Okay. This last question is a little different. The way that we can remove the discontinuity is we just kind of make our function continuous, right? And so if we want our function to be continuous, we need to have this function value defined, right? Because clearly our limit would exist from the left and the right, and we need our limit to also equal our function value. So to remove the discontinuity, we would want to define f of 2 as 4, right? Because if we were to do this, we'd be able to fill in that circle, okay? And so then this would just be a straight line, and we'd be good to go. Our function's continuous, f of 2 equals our limit, and everything is perfect, right? So that's just how you would remove that discontinuity. Right, 2 more examples, okay? Number 3, again, let's look. Is it continuous at x equals 3? So first step, f of 3 equals, if we look at 3, oh, there's an asymptote there. So again, that is undefined. So no, our function's not going to be continuous because f of 3 does not exist. There is an asymptote right there. Okay, so this is probably the graph of some sort of rational function. Throwing it back to your last unit or 2 units ago when we worked with asymptotes. So now we can go ahead and identify the types of discontinuity. So there are actually 2 on this one. So the first one that we see is we have this hole, right? So we have a removable discontinuity at x equals 0. And then our other one, oh, sorry, you guys can't see that, that's weird. Our other discontinuity is at that asymptote, right? So asymptote at x equals 3. Okay, and it's important to note which one is like your x values, where these discontinuities are occurring, when there are multiple of them, okay? All right, last question is about, again, our open intervals. So I like to just go through it again and draw our function. So if we start from the left, way in the left, we run into a problem at 0. So we have negative infinity to 0. We can go 0 to 3. That's where we want to run into our next problem. Alright, but then we can start back up again at 3 and keep going until infinity. The other way to look at it is like anywhere that you have a discontinuity, so a discontinuity x equals 0 and x equals 3, those are going to be our like problem values essentially in our open interval, right? So we had one at 0, our interval went from negative infinity to 0, 0 to 3, that was where we had our next issue, that's where we had our asymptote, and then from 3 to infinity. You go back up and look at this example. Our removable discontinuity was at x equals 2, and in our interval, that was the point in which we ran into our issue, right? We can go from negative infinity to 2 to infinity. Same thing up here at negative 1. Example 1, our jump discontinuity was at x equals negative 1, and so that was our point in our interval. Okay, that's just another way to look at it, if that works better for you in understanding that. Last example. Okay, so first up, this has a bunch of parts to it. Is this function continuous at x equals 1? So first step, we want to find f of 1. We look at our graph, tells us f of 1 equals 2. Alright, that's good. 2. We want the limit as x approaches 1 of f of x. Okay, we look at it. Our limit from the left equals negative 2. Our limit from the right also equals negative 2. Alright, so the limit exists. Our third step, we need our function value to equal our limit. 2 does not equal negative 2, so that's why it's discontinuous. So no, f of 1 does not equal the limit of f of x as x approaches 1. Okay. So now we can go ahead and identify the different types of discontinuities. I don't know why this corner piece keeps getting blocked out. I'm sorry, guys. The light, there we go. The light is just like super bright coming in from the window. So just like we did above, we have a bunch of different types of discontinuity. Actually, just one. But it's important to make sure you list all of them, right? So our discontinuity, if we look, we keep going. This isn't a problem. This is just piecewise, right? So you can keep going. Right here when x equals 1. The type of discontinuity, again, this is removable because we have a hole, right? So we have a removable discontinuity at x equals 1. So now we can use this, again, to write our interval for where it's continuous. So we can draw it from negative infinity all the way up to 1. That's where we run into our issue. A lot of people might think that this point might cause an issue just because there's a point. It's not. This was just, we'll get to this in the last step, but this is just a new definition from our piecewise function, right? So it's just, that's all that is. You can still draw this without picking up your pencil, right? Because it's already filled in, so that means you can just keep on going, right? But since we have this open circle and a point up there, that's where we're running into the issue, right? So we can continue this from 1 all the way to infinity, right? That's our interval. This last step wants us to define this whole function as a piecewise function. I don't think this is on your homework. I don't think it's going to be on like your assessment at all, so don't worry about this. This is more just like for conceptual understanding of like piecewise functions. I'm going to go through this, but please don't like freak out thinking that you're going to have to do this because it is a little tedious, but I just want you guys to see how it's done, right? Alright, so f of x equals, we're going to start out, I'm going to do these all in different colors so it's like extra clear what I'm talking about where. So first one is this little bit. I'm going to put this in green. So that's happening when x is less than or equal to negative 4. Okay. So what we're going to do is just kind of pretend like we can extend it. Alright, I can take out my little ruler. if I want to make this super official, right? And it looks like it's going to kind of go up towards 3, right? Looks like it's going to cross at 3, so we want this to be in y equals mx plus b form, right? Y equals mx plus b. A nice little throwback to like Algebra 1, pre-algebra, right? B is our y-intercept, so we know our y-intercept is 3. We'll have a plus 3 here, and then an x. And if we look at it to find our slope, I mean, it looks like it's about going up 1 over 1, up 1 over 1. Again, this is just an estimate. It's not going to be perfect. So this is it. Got 1x plus 3. That's our estimate for our first little part of the function. The next one I'll do here in pink. This is just a straight solid line from when x is between -4. -4 is less than x. Goes to an open circle at 2, or at x equals 1. So that's going to look like that. And since this is just a horizontal line, this is just going to be a constant, and it's just going to be -2. And that one's the easiest. There's no estimating what our function's going to look like. Next step is we need to define this point. Okay, so when x does equal 1, so x equals 1, we know that our y value is 2. Okay. So then our last little bit is just going to be this piece up top. Okay. And if we were to extend that, passes through -3, so that's good. So we have x minus 3. This is when x is greater than 1. And again, this looks roughly like it's doing up 1 over 1, up 1 over 1. So our slope is just going to be 1 again. Right? So that's our piecewise function. Hopefully, I know this video was on the longer side than what y'all have been used to, just because there is a lot going on in here. So hopefully this all makes sense. If you have any questions, let me know. I have my office hours Wednesdays and Fridays from 10 to 11:30. They have been incredibly quiet ever since corrections have been due for third quarter. So free people to pop in, feel free to email me. I'll see you guys in class Tuesday or Thursday. And yeah, your homework for this week is a Google form again, just like last week. All right, good luck.